Arindam Basu, Professor, Department of Electrical Engineering at City University of Hong Kong. Arindam Basu received his Bachelor of Technology and Master of Technology degrees in ECE from the IT Kharagpur, India, and MS and Master's degree in Mathematics and PhD degree in ECE from Georgia Institute of Technology, Atlanta, US. He's currently a professor within the Department of EE, City University of Hong Kong, and was tenured faculty at NTU Singapore previously. So that's a quite prestigious title. Dr. Basu was included in Georgia Tech Alumni Associate 40 Under 40 list in 2021. Lucky you. And awarded MIT Technology Review Top Researchers 35 Asia Pacific. Award in 2012 also received Prime Minister of India Gold Medal from the IT Kharagpur in 2005. He has students have several Best Paper awards in nominations at IEEE conferences. He has served as an IEEE CAS Distinguished Lecturer from 2016 to 2017 and currently serves in IEEE in various roles such as TC Chair, Associate Editor of Journals, and etc. So very excited, Arindam. So I'll hand it over to you. Thank you.
Thank you so much, Nick, and thanks to all the organizers for having me here. Today, I'm going to talk a little bit about the work that we have been doing over the last few years, where we use in-memory computing and dynamic vision sensors, a form of neuromorphic sensors, and use them to enable applications in the Internet of Video Things. Okay, so moving on, I'll start off a little bit by talking about, what are these neuromorphic technologies for tinyML and what really is the meaning of the word neuromorphic. So if you think about the word neuromorphic, which was coined by Professor Carver Mead in the 90s, what Carver was talking about was for applications in machine learning or pattern recognition, it would make sense for the computing hardware to follow the brain's computing hardware to use analog processing. Okay, for example, the brain uses voltages, currents, ionic concentrations to do this. And Carver's postulate was doing the same thing in silicon would allow us to have huge energy and area benefits. So that's really the circuit's definition of neuromorphic, where we are talking about the computation hardware being physical computing. Okay. But I call that neuromorphic version 1 because since then, the term has really broadened a bit. And I think Greg yesterday was also alluding to this. So today, if you go and talk with the computer architecture community, even digital designers would call their designs neuromorphic if their architecture is non-von Neumann. In other words, if the memory and the computing blocks are mixed together. Also, if you talk with computer science folks, people who are working with algorithms, they would talk about these algorithms of spiking neural networks where time is intrinsic to computing and people are using just this 1-bit impulses to do very sparse communication. So they would call that kind of algorithm as neuromorphic. Okay. So in today's talk, the two neuromorphic technologies I will talk about will be this non-von Neumann architecture where we mix memory and computing, and secondly, where the second part will be using these spikes or 1-bit signals in the special neuromorphic sensors. Okay, so a little bit of a background about the two technologies that I just talked about, dynamic vision sensors and in-memory computing. Firstly, dynamic vision sensors. You, of course, saw a lot of this in yesterday's keynote talk by Greg. But just to give you a background, these vision sensors are very different from how traditional frame-based cameras work in that these sensors have each pixel being operating asynchronously, and it detects changes in temporal contrast. This is very similar to how the human retina works. So if the change in contrast detected by this amplifier is larger than a certain threshold, then only you fire these events or 1-bit signals to the periphery and it gets read out by the peripheral circuits. Okay. If the change is larger than a positive threshold, then you give an on event. If it's lower than a negative threshold, then you give an off event. And you can kind of see how a continuous signal can be reconstructed from these, these signals, these 1-bit signals that show you how the gradient of the signal is changing. These systems have this advantage of reducing data because of the thresholding operation at the pixel itself. As a result, you can get very fast reactions in systems like robotics, where you need to sense data and react to it, do a motor command. So So the reason for this is because you have less data, you can read it out quickly. No need to wait for completing the frame. And since you have less data, you can process it quickly as well. In some sense, it leads to ideal sampling because objects that are moving very fast will be sampled faster. Objects that are moving slowly will be sampled slower. Okay, so as I say, a picture is worth 1,000 words. So we can take a look at a video of a scene where a pen is being flipped. So it's a very high-speed motion, and it's being captured by both a regular camera on the left and a neuromorphic camera in the middle pane. What you can see, the neuromorphic camera can capture the fast-moving object very nicely, right? There's no motion blur. But for a regular camera, you can see there's a lot of motion blur. On the other hand, the background, which is not changing, which doesn't have any new information, the neuromorphic camera does not sample it all the time, right? So it's suppressing the background and reducing data. Okay, so that's a huge benefit of these kind of cameras. The data format, though, is very different. You typically have bundles of these events where you have X and Y, which is the address of the event, P is the polarity, positive or negative, and T is the timestamp, the time at which this event happened. Okay, so that was about DVS. And the second technology I will be talking about in my talk today is in-memory computing. And the motivation for this is very nicely captured in this figure that's comparing the energy needed to do a compute versus energy needed to access the data from memory. For example, if you're doing 32-bit multiplications, you spend about 3.1 picojoule, whereas to get the two operands, the 64 bits of the operands from cache, 1 megabit cache, you would spend 100 picojoules, almost 30 times the energy, right? So that really shows you that memory access energy dominates. And that's why we are moving these days from a conventional system where memory and processing is separate towards a system on the right side where you just put the input X to the memory that's storing your data, and you directly get the result of the computation. You read the result out of the memory. So all the computing is happening within the memory. For in-memory computing, we of course have two choices depending on the type of memory, either volatile memory, SRAM, DRAM, or non-volatile memory like flash or RAM. My talk will talk about volatile memory or SRAM, DRAM based in-memory computing. The advantages of this kind of computing is this memory is ubiquitously available on chip, right? We have a bunch of SRAM and DRAM available all the time. It's a stable technology, mature one, very easy to use in CMOS. And of course, we have much lower write energy and higher endurance compared to NVM. The endurance is practically infinite for these, right? So therefore, they're good for learning systems as well, where you need to keep on updating the weights, keep on writing the weights. The disadvantage is we only have 1 bit per cell, whereas NVM like flash or RAM can have multi-bits per cell. And so therefore, we have an area overhead when we want to go to multi-bit designs. Also, producing multi-bit outputs is difficult by combining results from multiple of these memory cells. And of course, there's this problem of volatility. For example, DRAM, you need to refresh all the time. The particular example that I will talk about is we were thinking that, the data that you get from a camera or from a video sequence that you get from a camera, you typically store it on a SRAM or a DRAM buffer, right? And then this data gets sent to let's say, a deep neural network, which could be accelerated using RRAMs, non-volatile memory like RAM or flash, to get really very high throughput and very high energy efficiency on this DNN. But what we were thinking is, what if the memory that's storing this original image, if you could process the image using this buffer memory? For example, if I could remove noise and detect which frames are blank, I can turn off this following DNN for those blank frames. Also, if I could do region proposals, if I could find what part of the image has interesting information, I could trigger the following DNN to just operate on those parts instead of scanning through the whole image. Therefore, I could save a lot of energy at the system level by these approaches. And philosophically, this is similar to what we think goes on in the brain in terms of the dorsal and the ventral visual streams, where we think that dorsal visual stream really has a function where we look at where there is information in the whole visual scene, okay, so that you don't have to focus on everywhere. Okay? Kind of gives you an attention focus. So that's the sort of function we are trying to replicate using the in-memory computing techniques I'll show you later. So now coming on to the details, the technical details of the talk. So I'll be talking about this DVS, dynamic vision sensor, and in-memory computing for certain applications in the Internet of Video Things. And talking about the application first, of course, we all know that the number of cameras has been growing steadily, and they're in all our mobile devices. Also, for governments who are doing smart city projects, there's a bunch of camera strewn around the city for intelligent transportation systems and so on. So therefore, there's a huge need for us to really, sense, process, digitize, and store the data in an intelligent way to make this whole system scalable. In our case, we were looking at an application called unattended ground sensors, or UGS, where you need to deploy the sensors in a remote area to monitor traffic, to see who is coming in that remote area. Because it's a remote area, it has to be battery operated, and the data has to be sent wirelessly back to a base station. And this becomes a huge challenge for the visual modality of the sensing because of the huge bandwidth needed for visual data and the huge energy needed for wireless transmission. So typically the lifetime of these sensors for visual modality is like a month, right? So we want to extend that to a year. And to do that, we want to use dynamic vision sensors to compress the data, and then in-memory computing to process the data at the sensor very efficiently and only send some very short semantic information back to the base station. Of course, this same concept can be used for intelligent transportation systems in autonomous vehicles, for example, where you can send an early warning to a vehicle that, for example, a pedestrian is approaching the crossing and so on. Just to give you an idea what the final system looks like. So this is showing you an example of a Davis camera looking at an urban traffic scene. And you can see that, we can latch on to the cars, and each of the trackers can be sent to a classifier, and we can classify the type of vehicle. Okay, so that's the sort of system that we finally made. Okay, so coming now to the in-memory computing part, how we can use in-memory computing to exploit the temporal sparsity that's there in these neuromorphic vision sensors. So typically when we think about these event-driven vision sensors, we think, because it's event-driven, the processing should be very frugal. So we can use the events to trigger on an IoT process and then go back to sleep. But turns out this temporal sparsity is hard to exploit. For example, you can see here, this is a picture of cars moving, and at the bottom of the scene, there's some tree branches moving. You can see that even in the background, which it was supposed to suppress, there's a lot of events because of noise. So because of noise, it may be very difficult to duty cycle directly using these sensors. So our solution was to remove noise and then detect blank frames. The advantage is now across 3 different sites, we see that roughly 50% of the frames are empty. So I can actually turn down the DNN processor for 50% of the time if I can do this. Okay. So our solution was to store these binary events in a frame that we called event-based binary image. So it's still neuromorphic in the sense it has 1-bit information, but now we are creating the frames that's a little bit easier to handle in the IoT scenario. But now to detect the blank frames, I need some circuits. If I can do the blank frame detection, I get 2 times energy benefit because 50% frames are empty. But how do I overcome the blank frame detection overhead? Okay, so for us, we did entirely in-memory processing. So we got huge energy and time savings compared to von Neumann processing. Okay, so this is the in-memory computing advantage. We can get the actual 2x energy benefit at system level. So how do we do that? So firstly, to remove noise, because it's a binary image, we can use median filtering. Especially for binary image, this becomes a majority operation. Secondly, we did an approximate version of the median filter because it can be mapped to in-memory computing much better. And this is a recurring theme throughout the talk. Whenever you are mapping some algorithm to in-memory computing, you typically have to do a bit of software, hardware co-design, where you modify the algorithm so that it can match the computation kernels that you have. So in our case, instead of having a stride of 1, we had to modify the median filter to get a stride of n. Okay, so we call it non-overlap median filter, NOMF in short. So this is now coming on to the circuit details. I won't go into a lot of details, but again, you can ask me more if you're interested. This is the macro that we made. It's a 320 x 240 macro for QVGA image sensors. And we support filter sizes of 3 and 5, but of course, this can be modified. How do we do this filtering? That's very interesting. We exploit a phenomena called read disturb. That's very common problem in SRAMs. So how do we do that? Of course, we first pre-charge bit lines, which is like a standard read operation in SRAMs. For the word line, instead of enabling one word line, we enable n rows simultaneously. And that's the major difference in-memory computing, where you enable multiple word lines. Along with that, we actually short n column bit lines. So that's done by the circuits over here, which short the bit line and the bit line bars. What does that do? That allows us to actually have this n cross n image patch get connected together. So all the SRAM latches are now connected together and fighting against each other. Okay. So what happens in the fight is the majority cells will actually win. So if the majority of the cells are storing 1, they will actually flip the bits of the minority. This is a problem in typical SRAMs, but in our case, this is exactly the operation that we want, okay, for median filtering. And because all the banks are filtering in parallel, we can actually do this very quickly, okay, do the whole operation very quickly. So that's about exploiting temporal sparsity. And I'll show you the results later on. Secondly, we also did a solution based on SRAM in memory to exploit spatial sparsity. What is that? So we already saw that exploiting temporal redundancy can get us 2x energy savings. But what we see is average object size, in this case, in the non-empty frames, are roughly 5% of the frame. So therefore, there's a spatial redundancy. And if I can have an always on dedicated region of interest module that tells me where the objects are located, the following DNN can only scan through those locations. And we end up getting roughly 20x energy benefit at the system level by doing this. Conventional algorithms that do this are connected component labeling. And in fact, there was some work by Intel at SOVC 2020, where they used a von Neumann implementation to do this CCL algorithm. But of course, because it's von Neumann, you have higher execution time and memory access energy. So our solution was to do in-memory computing to do this region proposal. But of course, in that case, we had to modify the algorithm. We had to come up with some efficient algorithm based on histograms that can match the basic computing primitives provided by in-memory computing. So what is this histogram-based region proposal? What I'm showing here is an example of a screenshot from a DVS camera after removing noise. And you can see there are two objects. Because the background is eliminated, I can easily see the foreground objects. And then if I do summation across the pixels in the vertical and horizontal directions, I get some histograms. If I threshold the histograms, I can clearly see where on the y-axis objects are located, where on the x-axis objects are located. So intersection of these two gives me bounding boxes very easily. Okay. This can be mapped to in-memory computing very nicely, because summing across rows and columns is something that we can do very nicely in a memory. But there's a problem when there are multiple objects in the scene. You can see this car's bounding box is much bigger because of this bus. This is a fundamental problem because we are doing one-dimensional analysis of a two-dimensional image, and we came up with some algorithm to overcome this problem. Okay, now coming to the actual chip. In this case, the unit cell was 9 transistor SRAM. We had to add 3 extra transistors, N1, N2, and N3 to the 60 SRAM. N1 and N2 allows me to do a vertical read, and N1 and N3 allows me to do a horizontal read. So these cells are transposable. I can read the memory in both directions. And what this allows me to do with these horizontal and vertical reads allows me to get projections on the Y and the X axis. So this cartoon kind of shows you, if I project on the X axis, I can get locations on the X axis. If I project on the Y axis, I can get locations on the Y axis. So this projection is really getting me the histogram. As I mentioned, we had to come up with an algorithm called iterative and selective search to overcome the basic problem of overlapping projections. I'll intuitively show you how it works. So if you do a first projection on the x-axis, I get these locations on the x-axis where objects are located. That gives me a rough estimate. Now in the second iteration, I do the alternative thing by projecting on the y-axis. But when I do that, I only enable parts of the x-axis where I found objects in the last scan. So when I enable this, I get one projection. But when I enable the next location, I get 2 projections out, meaning 2 objects were combined in the earlier projection. Okay. So therefore, I can keep on iterating between x and y-axis projections by enabling each of the objects that I found in the last iteration. Okay. See, now when I enable this, I only get one projection. When I enable the last one, I only get one projection. So if for each enabling, I get only one projection out, I know my algorithm has converged and we have been able to separate out all of these overlapping objects. So just to show you how this works, this is an example of a video that's being input into our chip. And the chip, you can see, can directly output these red bounding boxes for all the objects in the scene. It's rejecting the noise and giving us the final location of the region. All of this is happening at energy per object less than 1 nanojoule. Okay. If you normalize and get energy efficiency, it's around 389 teraops per watt, and a throughput is around 400 plus giga operations per second. Okay. Compared with earlier work that used von Neumann computing, you can see our work on the left-hand side is orders of magnitude better in energy efficiency and processing time per pixel. Okay. So it really makes the overhead a lot less. Okay, the last thing that I want to talk about is a recent work in this space where we use a hybrid solution where we combine SRAM and DRAM together. And the motivation here was, the current work in literature that uses in-memory computing uses either SRAM or non-volatile, but does not mix them together. What about mixing them? Can we get some benefits? So we came up with a bit cell that's shown here. So in the bottom, we have a typical SRAM. The only difference is I have a transmission gate here that allows me to break the latch. Along with that, we have this transistor MS that can act like the capacitor for a DRAM. So this was, we call it hybrid RAM or HRAM because it's a DRAM and SRAM combined. The motivation is we can now use the DRAM, the charge on the DRAM for analog computing. We can do denoise, noise removal by diffusion. And at the same time, we can do the same region proposal by projection. We can reuse the same transistor MS that uses a capacitor in a different mode. We can actually use it for projecting on the X and the Y axis, okay, by using the source and the drain of the transistors. Just showing you one example here, the MS is being used as a capacitor. In the DRAM mode, I need to shut off the latch. So I use this transmission gate to shut off the latch. And in this case, it's really more acting like a set of resistors. These horizontal and vertical transistors are acting like resistors to diffuse the charge across bit cells in two directions. And you can see an example how the noise is getting removed. Okay. You can control the diffusion by changing the resistors or changing the diffusion enable time. And because this is analog operation, we actually, of course, had to do a lot of tests across PVT, across chips, across the center and corner of the chip, and so on. Secondly, this is showing you another mode where the same transistor MS can be used to do the same horizontal and vertical projections that I talked about. Okay, so I can just take one of the sides, in this case, the horizontal one, to VDD to do a projection along the other axis, and take the vertical side to VDD to do projection along the horizontal axis. By reusing the same transistor in two rolls, I can actually save the bit cell area. Again, because this is analog processing, we had to make sure across many different settings, the performance is robust. So this curve is showing you how we measure performance for region proposal using F1 score, which is combining precision and recall metrics, which is very common in the computer vision tracking community. And we can see that the result is actually much better performance compared to all earlier algorithms across PVT corners, across all settings. So the energy efficiency now is even higher than the earlier one. And this is because we are using charge mode computing, which is known to be the most energy efficient. Okay. So we hope that, now we can explore other options of doing this combined hybrid in-memory computing. For example, can we combine SRAM and RRAM? Can we combine other modes and so on? As a last step, I'm just going to show you where these designs stand in terms of energy efficiency. So this is a plot of energy efficiency on the x-axis and area efficiency on the y-axis. And this is a survey we had done in 2021, middle of 2021, and you can actually access the survey here. This is looking at all papers in ISSCC and SOVC till that time that were published that were doing neural network accelerators. And you can see that these designs that we had were actually much higher in energy efficiency and area efficiency compared to most other designs. Okay, so therefore these designs will not really be acting as an overhead if you use that to turn on a following a DNN processor. Okay, so let me just conclude my talk here. So hopefully I showed you that event-driven vision sensors are a great fit for Internet of Video things, because if you have a static camera, what I showed you, the background can be removed directly, and you can sense the motion directly at the pixel itself. If you have a dynamic camera, for example, if the camera is moving inside a car, the advantage you get is that a fast reaction. You can react and stop the car quickly if needed. You also have high dynamic range. Okay, allows you in many situations to get benefits. Secondly, I talked about in-memory computing as a key to ultra low energy and high throughput computing. And I showed you examples of volatile in-memory computing, which these are good for applications where you have frequent rewrites. For example, in our case, the image is getting written into the buffer every cycle, every frame. Lastly, I talked about hybrid in-memory computing as an exciting new direction where you can hopefully try to combine different modalities of the memory together. Okay. And with that, I come to the end of my talk, and I'll be happy to take any questions at this point. Thank you very much.
There's no questions at this point. Just for my sake, what software platforms, what things are you using to put some of these things together?
So if you're talking, there are two parts of this. First part is if you are talking about just optimizing the backend DNN processing, we are typically using the standard packages that you have in Python, like TensorFlow or Keras and so on. The other part, which is doing the processing live at the edge platform, in this case, we are using the entirely custom ASIC in our version to do the processing, so which is optimized using a typical digital design flow. As a first version, we had actually used an FPGA platform to validate the idea. Yeah.
Yep. See any? Oh, I think I've got one in there. This seems like a very okay. So it's anonymous. So this seems like a very niche problem, which is how you got the area and energy savings. How would this extend for other applications?
Okay, so that's a fair question. Now you see, we got these energy and area benefits for our particular processing, but what we are enabling is we are enabling a following processor to turn on or turn off. So really the energy benefits get passed on to the system level. So what I showed you at the end, if you're doing region proposals, you get roughly 20x energy benefit at the system level. So it's not really related only to our processor. Secondly, what we showed you is different computation algorithms being mapped to in-memory computing. Now, this I think is a very exciting area, because for neural networks, the most of the part that is being accelerated today is a matrix multiplication, which is very well understood. I think what's more interesting now is to see how you could modify other algorithms to match the in-memory computing kernels that we have and make these algorithms work better. So we showed you two different algorithms, noise removal and region proposal, which was not done previously. And we had to modify earlier algorithms to fit into this in-memory computing. So that's basically the message I want to pass on.
Thanks, Arindam. Mark Donaldson, an amazing talk. I have to rewatch. Question, what are some more intuitive connections between biological models done in silicon that you've come across that can be applied to more efficient computing systems in the sensor domain? That's actually a pretty good question. Yep.
Okay, so thanks. That's again a good question. It's a pretty broad one. So I think in general, the basic techniques that we found useful from biology are mostly related to attention. So if you can think about attention mechanisms either in the vision space or in audition space, because auditory attention, people talk about cocktail party problem all the time, right? So I think those are a lot largely untapped regions. We could probably take a lot from the attention mechanisms that we know and try to apply in different scenarios where it's very easy to apply, because you can think of the attention module as a wake-up signal, right? And you could just fit it into your already working IoT system. So I think that probably to me is the biggest low-hanging fruit that we can directly apply to our IoT platforms at the moment.
Thanks, Arindam. So thank you once again for your time. Thank you for that. Was a wonderful presentation. A final thank you to our sponsors. So once again, thank you, EduImpulse as a premier sponsor, Qualcomm, Syntiet, Deep Light, Clicktech, Renaissance, Actually, what I'll do is I will go through because it will cover all the sponsors in detail. So the premier sponsor, Edge Impulse, for those who have like to try a simple approach to, I guess, development on tinyML devices, Edge Impulse is a great solution for you. Executive sponsors, Qualcomm AI Research, again, a great organization that has most of the chips in most of the platforms around the world, and as well as some of their new software applications. Syntiate, making Edge AI a reality. Platinum sponsors, DeepLight, fastest video analytics solutions on ARM CPUs. Clickertech, global IoT solutions. Renesas, I guess, enabling a next generation of AI-powered solutions that will revolutionize every industry sector. Sony Semiconductors Corporation. Gold sponsors, analog devices, where what if becomes what is. ARM, again, ARM, large chipset provider as well, and they also have their own social nights, which you can join if you want to be more involved in the ARM community. PhotoHub, making over-the-air firmware models updates simple and accessible, especially important with all the sensors that require updates. Microsoft, providing, I guess, edge computing and the capabilities to integrate into edge or IoT or tinyML solutions into the Azure platform. NXP, again, a great hardware provider which integrates with the tinyML solutions. SenseML, an analytics toolkit suite for I guess, tinyML. STM Microelectronics, which provides extensive solutions to make machine learning easy. Engineering Exceptional Synaptics, engineering exceptional experiences. And silver sponsors, AOZip, Aeon Devices, EMSA, Greenwaves, Gravity, IBM, Imagimob, Itemis, Nota AI, OctoML, Prophecy, Quexo, Rexon, SAP, Silicon Labs, Stream Analyze, TDK. I guess before I finish off though, if people are interested in sponsoring, please reach out to the team. We're always happy to have more sponsors because it's with this sponsorship we can run such events. I just want to say a big thank you once again to the whole team, and thank you once again to the people who presented. Your content is key to making these communities grow. We're hoping next year we can have this in person. Don't forget, as we mentioned earlier, next year we'll be having the summit in San Fran. But thank you for all your help, and hopefully see you at the next tinyML session. Thank you, everyone.